welcome everyone to this latest Zero Carbon Mine webinar, where we've got Laurie and Jenny talking about, they've got a presentation they're going to share on decarbonising mineral processing. So I'll hand it over to them. They've got a presentation they're going to work through together. But yeah, if you've got any questions during the time, as they go through, please put them in the Q&A or probably the Q&A box, and we'll see if the guys can get to them as we go through. But other than that, I'll leave it to Laurie and Jenny to introduce themselves. They're probably better at that than I am. So yeah, hand it over.
Alrighty, thanks Brett. So my name's Laurie Reemeyer. I'm a professional engineer based in Vancouver, British Columbia, where it's raining as usual. I have a consulting business called Resourceful Paths, focusing on minerals processing engineering and sustainability, and been in the industry for just over 30 years now. I started my career at Mount Isa Mines and worked in base and precious metals, and got more into tailings, water, and sustainability issues, including greenhouse gas emissions reduction in more recent time. Okay.
Hi everybody, my name's Jenny Agnew. I work for Sedgman and have since actually graduated, so that's been 23 years in the industry now. And I've had the privilege of playing a lot of different roles over that time. So as a process engineer originally, then moving through managing all the ISO certifications for the business, managing risk, and now leading strategic development for the company, as well as the strategy for sustainability, and deciding what the really key things for us to focus on. And yeah, so it's been a pretty interesting ride, but pleased to be here with you today.
All right. So I think we're going to start really a bit big picture around greenhouse gas emissions reduction in the mining sector. And, the big end of town, if you like, the major mining companies through ICMM are probably really leading this this commitment. They've got various standards that the ICMM has adopted, including one around environmental performance, where it requires ICMM companies to commit to pursue continual improvement in environmental performance issues such as water stewardship, energy use, and climate change. It's bigger than that. It includes other things like tailings, waste management, biodiversity, etc. But you can see that climate change is specifically mentioned, and there's a sub-heading under that guideline there, that performance standard, that talks about implementing measures to improve energy efficiency and contribute to a low carbon future, and report the outcomes based on internationally recognised protocols for measuring greenhouse gas emissions, CO2 equivalent. So there's a bit to unpack there. We're going to focus today mainly on the mineral processing aspects of that, but you can see that there is an industry-wide commitment. And an example of the emission reduction goals comes from BHP there, where you can see they're talking about substantial reductions by the 2030 financial year, the medium-term targets there, and then eventually to net zero by 2050, which is, I think, at a corporate level, a lot of companies are committed to that. It's going to be hard work, but certainly BHP and other major mining companies have started down that journey, and we're going to cover some of that today. Jenny, I don't know if you want to sort of comment any further. I know there's more than just the ICMM in our sector, but they speak for some of the sector.
That's true. I mean, a lot of companies in the ICMM are kind of leading the way in that space, but other companies that aren't part of the ICMM are also doing things, but it's a pretty wide range on where people are at, I think, in that journey at the moment. And it's sometimes being driven also by legislation, which differs from jurisdiction to jurisdiction. So in Australia, we have the safeguard mechanism, which is definitely driving some additional focus in that space.
Yeah, and I think one other comment, Jenny, is you mentioned jurisdiction, and in some places where the commitments are a little firmer, in other places these are more sort of voluntary commitments. And then the question is, are the companies able to actually deliver on the commitments that they have made? And to be honest, the jury's out. And for certain commodities and certain types of processes, etc., it can be harder than in others to achieve some of those emissions reductions. So that is something, we need to think about this eyes wide open about the commitments the companies have made and whether they can achieve it, and what's the role of professionals like ourselves to help companies get there. All right, this next slide is an example of a driver tree, like where, it's a little bit small font, but the general gist of it is that there are various sort of branches of both emissions and metals production that can be used to determine what the overall kind of emissions intensity is. Now, this is an example for copper. So you can see on the left-hand side of the diagram, the end of the tree is a greenhouse gas emissions intensity in tonnes of CO2 equivalent per tonne of copper. And if we work our way back through the main branches, on the bottom branch, there's a branch around metal production, which is basically driven by how many tonnes of ore are processed, their head grade and the recoveries through the various processing stages. And on the top branch, essentially, there's a sum of various emissions. And in the mines, typical, say, open pit mines or big underground mines, you've got a couple of these main contributors to emissions. Diesel is a big one. Diesel used for various sort of haulage, in open pit mines, but the load and haul type of cycles are usually powered by diesel fleets and so forth, although some mines are starting to decarbonize those fleets and electrify them, etc. And then electricity. So electricity that's used in things like grinding and separation processes, etc., but also in things like material handling. And on this driver tree example, there's a few bubbles that talk about the various things that affect some of these key inputs. So we can see, for example, on something like the specific power input to an ore, like the amount of kilowatt hours per tonne of ore that we consume is affected by things like the ore characteristics, how hard the ore is, how complex and fine-grained the ore is, which determines how fine you need to grind, those type of parameters, as well as equipment decisions that you might make. So a driver tree like this is just a framework that can be used to understand where are the emissions coming from, how do they relate to key parameters that are determined by the flow sheet and process design and so forth. How do these things build up? And if you're going to try and reduce emissions, where are the big ones? So I don't know, Jenny, if you want to comment on this sort of approach a little bit more, or anything else on the diagram here.
I think it's just important to point out that the hotspots for every mine are going to be slightly different because the ore bodies are different, the jurisdiction's different, so the grid emissions are different, or it might be so far away from a grid that you have to power everything with diesel or some other option. So it's really helpful to actually get a bit specific when you're talking about any particular decision, because a general idea is good, but you really have to understand your particular mindset.
Yeah, so geography matters. I think I know when we were talking in the lead up to this, that was one of the comments that you kind of made, and we agreed on. Geography really matters around things like the source of electricity and emissions factor, and we'll talk a little bit more to that in a minute.
Yeah.
So here's an example of a copper gold mine, or gold copper mine, sorry, in New South Wales, Cadia, and we picked this one because it had quite thorough and granular emissions reporting. So as you're trying to understand the nature of emissions and possibilities for reducing emissions, not all sort of companies report to the same level of detail. Some sort of aggregate their assets, they slice and dice these things in different ways. But the former owner of Cadia, Newcrest, did some pretty detailed reporting. So we could sort of come up with some estimated emissions, and these are shown per tonne of ore milled. And what you can see is that in this case, the process emissions are dominant over the mining ones, and most of the emissions relate to electricity. We've got a couple of what we call scope 3 emissions in here, grinding media and lime. So scope 3 emissions relate to things that either inputs that you purchase, so something like grinding media that comes from steel, and steel takes quite a lot of carbon to make. We use metallurgical coal or coking coal in the production of steel, for example. So when you use grinding media and that's consumed in the process, that actually has some embedded emissions. The electricity in most cases is regarded as a Scope 2 emission, so that's purchase of electricity from the grid. In this particular example, we're excluding downstream transport and concentrate. So don't take this too literally as this is the total emissions from this mine, but it gives you a bit of an idea of the breakdown. Okay, and as Jenny said earlier, very case specific, right? Because this is a block cave mine. The diesel emissions from this mine are a bit lower than normal. Okay, so here's a pie chart, and we can see electricity is dominating, and a couple of things here. The emissions factor, this is from New South Wales. In this particular year, 2022, the emissions factor that Newcrest quoted is 0.79 tonnes of CO2 per megawatt hour, which is consistent with a grid dominated by coal. And things are changing in Australia. We'll see that in a moment, but that's one of the main reasons why emissions from this mine are so high. And you can see the process electricity emissions dominating. And just a comment there that about 2/3 of those processing electricity emissions come from comminution, so crushing and grinding and so forth. Any other sort of comments on this one, Jenny?
No, I think we'll go through to talk about the variation on the emissions factors depending on which part of Australia or the world that you're in. So this diagram shows the emissions intensity depending on the type of fuel used, and you'll see that where it's a coal-dominated grid, the emissions are going to be a fair bit higher. In places like British Columbia in Canada, where Laurie is, they're really, really low because that's dominated by hydroelectricity. So decisions that you'll make in one part of the world can be quite different to decision you'll make in another part of the world if you're trying to reduce your emissions, taking that into account. We did design of a gold plant at one point for British Columbia, and the gold circuit was electrified, and I got very curious and asked the question, well, what if that was in Australia, or if it was in South Australia, would that same decision be made? And the answer was no, it would not. It's actually more emissions intensive to electrify that circuit. So it's really important to understand the impacts of the emissions factor and do a little bit of crystal ball gazing about how that's predicted to change over time to understand, the sensitivity of that decision to the grid over time as well.
Yeah, and just to that point, Jenny, we were talking about the CADIA emissions from 2022, and remember that number 0.79 tonnes per megawatt hour of CO2 equivalent. These are data from the ICMM, the national operator of the Eastern Australian grid. You can see that in the last 12 months, the emissions factor for New South Wales actually dropped to 0.66. And that's because the amount of coal that the proportion of coal is actually starting to reduce. So over time, those emissions factors in Australia are definitely reducing as renewables increase and the coal plants are being retired.
Yeah. So we're going to talk about a few different options when we're trying to reduce emissions in processing. And the first is we saw how big the impact of energy is in the emissions mix for a typical mine. So reducing how much power we consume is definitely one of the levers that can be used. This can be done in a few different kind of hotspots along the mining value chain, and some of them are in the mining space. And even though we're talking about processing right now, Laurie and I were discussing how important it is to not just think about the processing plant or the mining part in isolation, that they're so interconnected, and decisions you make in one area highly influence the energy and emissions in another part. So it's important to think of it as a whole system. So for instance, selective mining, such as shovel-based sensing, can be a way of reducing the ore transported and the ore crushed, which takes so much energy. And that can be a decision that's made at study phase, but it's also something that is potentially able to be implemented in operational phase. And some of these decisions, need a bit more data than you may have at study phase. So the ease of convincing the people with the cash to do these projects may be easier once you actually have some operational data behind you. Another option in that space is ore pre-concentration. It is a bit dependent on the properties of the ore, whether sensor-based sorting is applicable, but where it will work, it can be pretty impactful because you can reject waste at the pit rather than transport it to the processing facility. And that's particularly important where you're thinking about ore bodies that might be getting further and further away from the processing plant, or where you have satellite ore bodies that are being explored where there's an existing central processing facility. Another option is coarse particle flotation. I'm not sure if you want to take that one on, Laurie. Or I can.
Yeah, we'll have some pictures later on where we talk about that one a little bit. But the concept of coarser separation and particularly coarse particle flotation is that if it's suitable for your particular ore type, then it's a good idea to try and reduce the amount of grinding energy that you use and not to grind any finer than you need to reject a lot of the gangue minerals that you're trying to reject. So as a principle, if we can do separation at coarser sizes and reject material that has very low valuable mineral content, that's a good way of saving energy. But you've got to make sure that you understand if that type of approach will work for your ore body.
Test work. The next option is more efficient comminution machines and process machines, and that's there's so much energy that goes into making big rocks into very, very small rocks to allow us to capture the value. And excuse me, there are a number of exciting emerging comminution technologies, and we'll touch on them a bit later. And some of them have really got some promising reductions in the amount of energy that gets used in that process. As we were speaking about before, the next way is to reduce the emissions factor on the energy you are using. So if you can build your plant in BC, go for your life. But often you can't move ore bodies. So we're stuck with where we are, but there are options. There's power purchase agreements with providers of renewable energy that a lot of companies are entering into to reduce their emissions for their mine. Some are also going behind the grid and installing their own renewable energy onto mine sites. The length of time that your mine is planned to operate is impactful on those decisions, because if it's less than 20 years, you can't put wind up. So, yeah. And the other thing that's not common at this stage, but people are definitely thinking about it, is demand side flexibility in terms of mining and processing. So that means if the energy at a particular time of day is super expensive, which is generally because there's no renewables left and everyone's trying to use what's being stored in batteries and places, that means that if you can source some of your own energy to remove your demand away from that peak load, you can potentially be flexible in chasing lower price for your energy, as well as helping to improve the penetration of the renewables that are there. That's not so easy when you've got SAG mills in your circuit, but there are some of the newer comminution technologies that allow a bit more flexibility in terms of flow through that circuit. And then reducing embedded carbon in consumables. So we've been speaking about the high impact of mill media. So you can choose different mill media that have different impacts, but you can also have an explore, unless you've already installed a SAG mill, in which case that might be difficult. Choose a different alternate technology for that circuit that has a lower impact in terms of the consumables. And there's also some other reagents that tend to have a fair impact. Lime's one of them, depending on the processing circuit. Sometimes flocculant makes a bit of enough of a blip to start looking there. So that's definitely another place to look. Any other comments on these?
Yeah, I'll make a couple of comments, Jenny. Sometimes when we're thinking about comminution systems and alternatives, for example, there's a couple of places where these things might come up. So if you think about, for example, a circuit using high pressure grinding rolls, we know that in general that technology is more efficient. The compression breakage is more efficient than tumbling mills. However, you usually have conveyors, so you've got to sort of weigh up a reduction in the power consumption of the breakage unit with the additional loads that come from conveyors, and then you can think about how grinding media consumption will reduce because you've now got these rolls, and if they're well designed, they last quite a long time. You don't have to use the steel, so there's sort of ups and downs, and you've got to kind of weigh up the different benefits and costs that go with that sort of a change. And then both, is it economically worth it? And what's the net impact on your emissions? So it's quite important that you're looking at these things as a system, because otherwise, you can kind of get a bit of a false impression around whether a particular alternative is the right thing to do or not. The other comment I'd make about the shovel-based sensing, so just a little bit more background on that. So there's a company here in BC called MindSense, and it's developed this system. It's called ShovelSense. And what they do is they have XRF detectors on the shovel bucket, and they're basically using that to infer what the grade is on a bucket by bucket basis. And that has been applied to a number of mines in BC and in South America. And I think it's being, looked at increasingly in different parts of the world. And, it does look pretty interesting, right? There's more resolution that you can get on a shovel bucket by bucket basis than in a typical block model, right? Block models are often like 20 meters by 20 meters, etc. So there's many kind of shovel bucket loads within each ore block, and so sometimes with these types of innovations, it's like the data you get from the operating practice, like when you're actually in there with some sensors and measurements, that helps you understand what the value proposition is. And so at one mine here in BC, for example, with ShovelSense, they got much better resolution about some low-grade dikes that were running through their copper porphyry ore body, for example, and that helped them to do more selective mining. So there are opportunities there, but some of that has to be sort of done through good operational practice once you're starting to get into the operating phase, I think, as Jenny alluded to. Look, I'll make one other comment. We haven't sort of talked about it too much here, but there are some hard to abate type of emissions for certain types of processes and commodities and so forth. So if you think about things like pressure leaching circuits that, for example, require large amounts of limestone, they're also potentially high pressure, high temperature, etc. So they need process heat, etc. Some of those type of circuits, they're hard to abate using conventional technologies. And so part of that's a bit of a longer term play around can you modify those flow sheets, those technologies, etc., to not have to be so intense with energy, with consumables. How might we, need less limestone, for example, in certain complex or refractory gold processing flow sheets, for example, because all these things contribute to emissions. So not all of these things are easy. For a circuit that has, predominantly electricity for grinding, there is a pathway, right? It's renewables. Whereas for a mine like Pueblo, I can never say it, Pueblo Viejo in the Dominican Republic, they use enormous amounts of limestone in their neutralization. Very hard to abate. So it's not always easy. And that's why sometimes we got to work on longer term technologies to get better economic and environmental outcomes.
Just quickly, guys, yes. We had a question from Alvin on is the industry moving towards a standardization of measurement and calculation methods for determining the inputs and outputs? Like, is there a standard around that?
Yeah, I mean, the most commonly used one, well, in Australia, we've got the ENGA standard, which, mines have to generally report to that, and the upcoming additional financial reporting that goes along with that now. But globally, the GHG protocol is pretty widely adopted standard.
Yeah, and Jenny, I'd sort of say a couple more things. The ICMM certainly has been working around a standard around Scope 3 emissions, and that's a really, really big deal, particularly for steelmaking materials, right? Because the majority of emissions associated with things like iron ore are actually like downstream, the downstream processing into steel. So that's coming. I think in different parts of the world, there are generally emissions factors that are issued by regulatory bodies. So in Canada here, for example, we can look up information from the provincial governments around what the emissions factor is for the grid. And then they sometimes have, for example, what's the emissions factor for key inputs like lime, like cement, and so forth. So there is a methodology. But like one of the things that Jenny and I were talking about in the lead up was as professionals, we also need to get a little bit more informed about some of those things, right? Like it's not just about sort of saying, oh, there's going to be some environmental consultant who'll calculate that for you. You really want to be somewhat familiar with some of the metrics, a bit like what we talk about today. You know, if you're in a particular part of the world, do you know roughly what the emissions factor is for electricity? It'd be good to know if you're like near 0.01 or if you're near 1 or more. Like that sort of stuff is generally good to know. So you've got an idea of where your levers are.
That's right. And if you've got, an operating facility and you've got suppliers that are providing your high, like consumables that you use a lot of, you can ask them what work that they've done on their emissions profile. There's a thing called an environmental product declaration, which you can ask for from suppliers. Some of them will have them, some of them will not. But it's a good question to ask. And when you're purchasing steel, there are definitely suppliers that do have that information for particular products. So definitely something to start wrapping your head around. There is software that can help you with that and give you access more easily into some of the databases that exist in the world for emissions factors for a whole load of things from limestone to acid to anything else that might be part of your process. So and some of them are starting to emerge that are actually tailored to mining and processing, which makes it a little bit easier to do the work. A lot of software today has been very focused on the infrastructure sector and construction, but in the mining sector, and I've done a couple of calcs to really make sure I understood this well, is the construction in a hard rock mine is less than 5% of the lifetime emissions of the processing facility. So whilst it's really helpful to reduce the amount of concrete and the emissions of your concrete and your steel in your plant, the processing decisions that you make that influence energy and consumables are much more impactful. Hopefully that answers the question. So now we're going to talk a little bit about collaboration in this space and some work that's been happening recently that's pretty exciting in my view, because as we've been speaking about, the comminution energy impact in mining globally is significant, and anything that we can do as an industry to reduce that impact has an impact on global emissions. And one of those things that's been happening recently is BHP held a kind of innovation cohort around comminution, and there was 10 or 12 companies involved that brought their technologies to the table that were selected to be involved. And the process involved looking at each of these technologies, exploring them together, and working out where they fit in circuits and what other parts of the system they impacted. And I think some of the aha moments were around how some of these could actually be synergist with each other and provide benefit when you put them together. Some of the technologies are around the ore pre-treatment, whether that's in the ground before it's hauled or at the plant, with ways of fracturing or weakening the ore along the boundaries, grain boundaries. So there was microwave technologies, high voltage, plasma, supercritical CO2 as some of the technologies that were involved. There's also quite a number of novel comminution devices that have a much lower energy use per tonne of ore. and they're at various technology readiness levels at the moment. So some of them are still pretty hush-hush and secret because they're very early in their development, and some of them are more widely known and on the market. But and there was also a high-pressure slurry abrasion technology, and Sedgman team had the privilege of supporting BHP in kind of coordinating that cohort, and it was really exciting work. And you know, the next phase is choosing some of those to take forward to do more test work, particularly with some BHP data and samples, I think. So it's exciting work, and it's looking forward to seeing where that goes. And I'll definitely make a comment on collaboration in this space is so critical. This is a problem that's not just one company's problem, one mine site's problem. It's a common thing, and finding ways to get around IP issues and come up with a solution that can be shared with the industry is so critical to moving quickly on this. So it's really pleasing to see that that's starting to happen, and the way that those cohorts are working is definitely a step in the right direction.
Thanks, Jenny. And I'm just going to talk to the photo of the big check. So this was a check that was presented at PDAC recently here in Canada, PDAC being the biggest mining really conference event, regular conference event in the world in Toronto. So this is the Future of Mining Challenge from Wheaton Precious Metals. I was one of the evaluators for this challenge. It was a basically $1 million prize, 1 million US, I think it was, a $1 million prize for technologies that reduce greenhouse gas emissions in mining substantially. And the winner was a comminution technology. It's rethink milling. We'll see some pictures in a minute of their new kind of comminution device. But we assessed a number of different types of technologies at in this case, they picked a technology readiness level. So they were not looking for very early stage research projects. They were not looking for things that were, already kind of ready for commercialization as such. So in this case, it was technology readiness 5 to 7. And I think the hope is that this $1 million prize will help this particular technology advance and hopefully be brought into demonstration scale and ultimately into production in plants. So there are a number of these sorts of prizes. Some have been funded by groups like BHP, for example, in various initiatives. And I think for any emerging technology firms, it's always good to look out for these sorts of opportunities.
Yep. So
All right.
here's
So
a few pictures of some of the machines. Yeah, we've got HPGR rolls, G rolls up top, and yeah, sorry, HPGR there.
The cam mill in the middle.
Yeah.
And then the thing on the green on the bottom right is the mono roll. Sorry, so that's one of the other rethink milling technologies. But I think key thing that sort of stood out to me on some of these machines, Jenny, is that the configuration's a bit different. So particularly when you look at the cam mill and the mono roll, you've got, rather than tumbling balls, etc., you've got this, ore is coming into, it's going to be coming into pinch points of these rotating gear type of assemblies, which is a little different. There's different sort of material handling aspects to that. There's going to be some interesting things around scale up, how you handle certain sticky ores, all that sort of stuff. So, I guess we're going to see how all this goes.
For sure. And then we're going to move on and have a little chat about coarse particle flotation technology. You mentioned a bit more about that earlier, Laurie, so I'll let you continue.
Yeah, thanks. Yeah, so there's a couple of examples here of some of the emerging machines. So on the left, you've got the NovaCell, which is a machine that was devised by Professor Jamieson from the University of Newcastle, and currently sort of I think under like demonstration at a mine in Chile. They've got a unit that's operating there. It seems to be reasonably successful. In the middle there, we've got the Aries Hydrofloat. This is an installation in North America pilot sort of scale. You can see it's pretty large, but it's a pilot scale installation. But that has been put in commercial production at Cadia, the mine we talked about earlier, as well as El Soldado in Chile. And then on the right is a machine from FLS, which is called the Corsair. So a number of providers that are using these types of technologies. They have some similar themes, which is that they're no longer just relying on bubble sort of, how do I say it, lift from bubbles. They're also working with the hydrodynamics to essentially get some sort of a flow that allows coarse particles to attach to bubbles and be recovered at high recovery rates. And the important thing to consider here, firstly, the configuration of the cells is a little different. You need to be thinking about the regrind requirements, because you'll generate low-grade concentrates at coarse sizes that need some additional regrinding work. That's all part of the assessment of whether this type of approach would work on your ore. And you need to be ready to deal with much coarser slurries, which have various challenges around sanding and blockage, as well as abrasion and so forth. So these sorts of manufacturers have been working through some of these challenges with the sites that they've been operating at. And in general, I think it's important to share knowledge where possible around whether these types of technologies are suitable, and to work with the vendors and others to consider where they're applicable.
Yeah. And the other thing I might note, if we're doing a bit of systems thinking, is if you've got a coarser tailings, that means it's slightly easier to dewater, which can change how much energy you need to use if you're working, particularly aiming for a dry tailings as well. So, yeah.
Yeah, and that sort of leads into the next slide there, where we've got this example from the El Soldado mine, Anglo-American in Chile. This is the practice called hydraulic dewatered stacking, which is taking the coarse tailings from the hydrofloat, the coarse particle flotation, and placing them in particular ways to allow better drainage. So that's to the point that Jenny was just making. So this next one is also about other types of flotation machines that have smaller footprint and lower power requirements. I think you made the point earlier, Jenny, that while machines like this allow us to use less steel and concrete, and that does reduce emissions, the big game is really, can they also reduce power consumption? And generally these sort of machines do. So we've got the Jamison cell on the left, we've got the Concord cell, which is also pneumatic, but has elements of Jamison's type of technology also. So those two are both Professor Jamison related inventions. And then the stack cell, which is another type of machine. There's a few others, but the key thing really being, determining if these types of technologies are suitable for your ore and your flow sheet, and then how you might take advantage of the smaller footprint and the lower power requirements, and assessing that on both a sustainability metric as well as an economic metric.
So we thought, well, what are the main challenges to implementing some of these things that look so fantastic? And one which we kind of touched on earlier is having, what stage in the development of a new mine do you have the right data to make that decision? Some of them can be retrofitted if you're talking about ideas such as shovel sense, and you may have the right data to help make that decision once you're in operations. Other decisions really you need to work out before you make the decision on the layout and concept for a facility, because you cannot change that decision without spending a lot of money later. For instance, the type of comminution machine that you choose has a big impact on the layout of all the materials handling facilities around it, and the footings and everything that's required. So doing the test work early enough to make those decisions well is critical, and making sure that we've thought about representative sampling across the ore body to really understand the potential impact of the change of the ore body over time as well. The other challenge is that putting a new technology into a flow sheet and then going for funding can be challenging. It's much easier to get something funded if we've already done it 50 times already. But that doesn't lead us down the path that we're aiming for in terms of reducing the impact of the industry and the emissions intensity of the metals and ores that we're producing. There's also the barrier that happens with the solid thinking between mining and processing. Like, we all know our domain well, but we have slightly different drivers. So having those people actually talking to each other, particularly when we're developing the concept for a new plant, but also during operations, to be optimizing all of the parts of the value chain. And I don't know, Laura, if you want to talk about that next dot point.
Yeah, so I think it is quite important that that mining companies and engineering companies are sort of clear around, what is their capability in particular areas. So I think a lot of the mining companies have started to build internal capability, particularly the ones like ICMM that have commitments to emissions reduction and so forth. But not all mining companies have the resources or the capability to even understand some of these things. Similarly with engineering companies, some engineering companies have greater capability in certain process technologies. Maybe they've worked on the design and implementation of coarse particle flotation, where others may not be familiar with those types of concepts. And if you want to be successful, you do need to take all of those sort of things into consideration, right? Because some of these emerging technologies and process flow sheet changes, they have some pitfalls. You've got to have the relevant experience. You've got to be learning what you can from operating sites and so forth. So, thinking about those things is important. Thinking about the optionality, to the points that Jenny made earlier, sometimes it's hard to justify a particular process change right away, but perhaps you leave yourself some room for expanding a circuit later with sensor-based particle sorting, or maybe you leave some room for potential future integration of a hydrofloat once you've got some more data, when you know that the head grade of your ore is dropping and things like that. So making sure that you haven't forgotten about those types of possibilities. It is important for each mining company to be clear also about its appetite for risk. And so I think we've seen some companies, we see that certainly in places like Australia, that some companies have really invested in some particular technologies and have been leaders. When we talk about, for example, the former Newcrest, we talk about Anglo American, these are companies that have invested in some of these newer technologies, and they've invested, significant amounts of money, tens of millions of dollars. Not every company is ready to do that. And sometimes it's a race to be second. But, it is important that, if you're not that brave to be the first, that at least you're staying informed and getting on the bus as some of these, successful technologies emerging, if they're suitable for your body.
Yeah, I'll just echo that point around optionality. If you don't have the data to make that big call now, what could plan B look like? And can you design your plant to be able to integrate that more easily in 10 years' time, for instance? It is a really important question, because it can mean go or no go at that decision later if you've left space for that.
Yeah, absolutely. And just a general comment, you've touched on it already, Jenny, in terms of funders, but economics do matter in these sort of projects, and sometimes a way around that is to seek sources of capital where sustainability metrics are part of their criteria. So the investment in collaboration, working with OEMs, for example, on emerging technologies, etc. Being on the lookout for banks and lenders and governments that look to support low carbon technologies. There are options there, but sometimes you've got to put in some work to find them.
Just got a question that just popped up about to support new decisions, are there any market-ready sensing technologies to help with data-driven decisions? So you've gone around a lot around, what data, having the data to make decisions. I suppose it's what technologies help with that.
Yeah. There are quite a few in the market. The shovel sensors market ready, and there are, inline ore analyzers that, depending on the ore body, that might be applicable and are being used. I know there's one in use in Queensland at a tungsten mine doing inline ore sorting to reject gangue before it gets crushed. So definitely that. And then inside the processing plant, there's definitely OEMs as well as engineering and other service providers. Sedgman's one of them that can install sensors that put data to the cloud and have experts looking at that data to help analyze that to make good decisions. So definitely there are a lot of options available and being developed all the time.
Thank you.
Great. And I guess closing out, I love this diagram because this is about when you make decisions and how helpful it is. So in terms of choosing a concept that's going to have a step change sustainability from business as usual, the earlier in the development of that project those options are looked at, analysed well, and a decision made really does change the outcome. Once you get into the later stages of detailed design, don't really have the opportunity to do a massive flip on your processing choices. That really needs to be done a fair bit earlier, and it can have a big impact. So, and that's also when you can look at opportunity and do a bit of sensitivity analysis to say the change in carbon price over time and how that affects the economics. Any other thoughts there, Laurie?
Look, I think this concept of optionality also sort of lingers there a little bit because there's certain big things that are locked in, and projects need to continue to go forward, etc. Sometimes you have to make decisions at a particular point in time based on the best knowledge of what's available at the time. It's always a good idea to understand, what potential might be to pivot later on. So if you have, for example, a particular footprint, you have a particular technology that you adopted. In some cases, like, for example, new generation flotation machines, you can kind of slot them into the space that you're gonna put them. But in other cases, like with some of the alternative comminution technologies, not really. Like an HPGR circuit and configuration is completely different to a SAG mill. And so if you committed a design for a SAG mill and you want your project to stay on track, well, that's not an easy switch. So understanding this diagram also in the context of optionality, I think, is important. If you're going to sort of change courses or whatever, understand what the impacts are on your project schedule and cost. And whether you think it's worth it.
Yep. And, the next point is just really doing the work, which, once you're doing an operating cost estimate for any of the options that you're looking at, it's not much of a step further to put some emissions factors against those and understand the carbon and other impacts of those decisions. And it's historically we're comparing options on CapEx and OpEx, but I would encourage us all to see if we can also do it on CarbonX as well. Anytime we're doing an optioneering study. I see Wilco's put a comment in the chat about the scalable and adaptable challenge, which is a similar innovation project that was done with the Think and Act Differently team with BHP, or was Oz Minerals at the time. And that was a really interesting project as well. So it was collaborators from all across the mining value chain trying to answer the question, what if you had a mine that was remote and had to run off renewables? If it was all electrified, what could you do differently to make that work? And the interesting output was that it probably would not run 24/7. There was a simulation built that was actually energy constrained, and the output was that the sometimes the mining took all the energy, and other times processing used, around 24/7, and sometimes it didn't, particularly in winter when there wasn't as much sun around. So super interesting exercise, but just that modelling concept to look at lots of different options, I think, is something that as an industry we could do a lot more of, rather than just one option that we cost out in great detail without looking at all of the different potential scenarios. The world's pretty changeable at the moment. So understanding the impact of the different drivers on economics is super important. That's us.
Sorry, Jenny. Just following on from that question around that scalable adaptable challenge. Do you think there are many companies that are really looking at being flexible like that and really doing things differently, or is it still a bit of a
I'll lean back on the challenges that we spoke about just before. Getting the funders or the final investment decision makers across the line there can be challenging because it's a risk. If it's not been ever done before by anyone else. That concept had been developed for a project that's being paused at the moment, but it was getting there in terms of having a different comminution set up to allow for more renewable penetration with a bit of demand response flexibility. But I think we've got a long way to go before that's the norm.
Yeah, and I'd probably just add to that. I think part of it is around, any industry that is capital intensive, the conventional thinking is that you've got to utilize that asset at a very high rate. And, part of what I think innovators in the mining sector need to be thinking about is, does it always need to be that way? Are there other solutions that might be not as capital intensive, but a bit more flexible, perhaps with higher operating cost, but where there's different cost drivers, and in certain cases, like if there's really cheap energy, for example, can you offset that nominal high operating cost and operate economically in a different way? I think we're just going to be a little bit open to that, but it probably means that the conventional kind of really big economies of scale, etc., types of designs we conventionally do may not work for that model. It might have to be something different.
That's right. And I guess ore bodies are changing too in terms of what's available now. We've mined out all the easy ones for the most part, and the ones that are coming online are deeper, lower grade. They're satellite ore bodies, and there has to be different approaches for some of those. The conventional way won't really stack up economically. So that's where options for relocatable modular facilities that do one satellite ore body and then go on to the next one, and it's paid off over a number of different sites, may be things that we need to start considering.
Do we have any more questions out there? You covered a lot in that presentation. I think a lot of ground there. Just saying, is anyone got any questions? Just type them in if you do. Main thing I think I took out of that is that there's lots of different moving parts, so it's not a one size fits all. Definitely a case by case, looking at what the technologies are. But I think the comminution side is definitely a big part of the equation. Are the technologies you see on that side that are close, to being ready to be, implemented on, wider scale?
Some are, and others are, around the 5 to technology or 7. Some are even earlier. It's a bit of a range.
Yeah, I think I'd make the comment as well, Jenny, that the integration is still a bit of an open question, right? When we were going through the Wheaton Prize, in a general sense, one of the things that came up is, how does material handling at large scale integrate with some of these machines? And what scale could this realistically be done? There's a big difference between machines that can handle, say, a few hundred tons an hour with ones that can handle a couple of thousand tons per hour. And that also goes with things like particle sensor-based particle sorting. Like you've got machines that can handle maybe 150 tonne an hour per machine. But if you've got a gigantic mine, do you really want to have 20 trains? Or can we scale these things up to be bigger? So I think the jury's out on some of these devices, just to see how well they can scale up. And in the meantime, it would be interesting to see if there's niche applications that are, smaller and moderate scales that are still good, right? Still compelling economic opportunities.
That's right. And so, like, some mine sites are looking at maybe we can trial some of these at an operating mine with the off-take stream from one part of the thing, which is a fantastic way to de-risk testing out. So that's definitely something that's kind of happening, but there's a lot of work in that integration piece is critical. Just because you've got a machine that works well, if it doesn't integrate well into the whole value chain, then it's not going to fly.
Oh, thanks, Laurie and Jenny. I don't think there's any more questions. So thanks for your presentation. Like I said, you covered a lot of ground there, a lot to watch out for, and hopefully we start seeing some of that technology coming through. So we had one question, and we've not been able to share those slides. Is that be possible, Laurie, Jenny?
Yeah, I think that's fine, right, Jenny? Are you comfortable?
Yep. You've got your brand on them, so I'm good.
No worries. Yeah. Okay, so that's fine. We'll send that through to you, Brett, to distribute.
Yep, no worries. And so I'll call it there, but we've got another webinar, similar time next week, where we're talking about simulation technology for mining, decarb. So it'll be another interesting one. We've got Adam Price from RPM Global and Jacob Bennett from Innovation Industries talking about simulation. So tune in for that one. And other than that, have a good day, and we'll catch you next time.
Thanks, everybody.
Thank you.
Thank you.